A couple things first. It looks like I'm going to have to be out of town on Monday. So I'll keep you updated on this, but it looks like no class Monday. And then next week, I think, is when we have the, whatever they call it, the fall break, right? And that's Wednesday, Thursday, Friday. So it looks like we're probably not going to have any class or lab next week. Okay, before I get into new stuff, does anyone have any homework questions you want me to go over? Okay, the weekly assignment is graded. So look that over, and I'm going to get up another weekly assignment soon. I guess I definitely want to get that up before next week, so you have something to do, but okay. What we were talking about last time, if you remember, we started talking about, so back to 2D particle kinetics. And kinetics means combining kinematics that we were doing before with the causes of motion. And so for now, that's mass and force. And so I defined mass and force, and we used Newton's second law, which is the biggest equation in this whole class, to surprisingly successfully kind of figure out how hard gravity pulls on things. And it turns out gravity pulls on things in proportion to their mass, although mass and weight are different, The force gravity applies and the mass are two different things. And so now we're just going to, like today, we're just going to keep talking about all the other kinds of force so that we can, so that we're able to, whatever kind of force is applied to a body, we can put that into our problems and do calculations with Newton's second law. So remember I said there are four types of forces that we're going to see. And they kind of go roughly into two categories. The first category is the weight. And actually, the weight is one of several forces that you can think of as, we'll talk about them later, as field forces, force fields. In Super Friends or whatever, force fields are really cool. In physics, force fields are actually kind of boring. Weight is one of them. It's just saying that the object's location is enough information to know what force is applied. And so weight fits into that category. Some others that we're not going to deal with in this class, but you would see in Physics 2 if you took it, are electric fields, magnetic fields. And then the second category is contact forces. And we're going to have three of these. So the first one is pushing contact. So what happens when two objects are pushing on each other? The second one is pulling contact. And even though you can pull on something without attaching a cable to it, we're going to think of this as always being cables or strings. So like if you grab someone's shirt and pulled on it, you could apply that same force to them by hooking a string or a cable up to their shirt and pulling on that. And so we're going to just always think of pulling forces that way. And then the last one is friction forces. And before I get into, so we've talked about what the weight force is. No matter what the object's doing, if it's sitting at rest or if it's moving, flying through the air, that weight force is always just the mass times the acceleration of gravity, and it always acts down. So even if the object's flying to the side, the weight is down. Okay. So before I get into the other ones, I'm going to talk about something that we're going to use to keep our forces straight. And this is really important. You're going to have to do this before you use Newton's second law. So anytime you use Newton's second law, you must draw a free body diagram. And I'm going to always abbreviate that FBD, free body diagram. And the meaning of that is you take the object that you're considering out of the context of its surroundings and you make just a simple diagram of it with the forces on it. And for complicated problems, it makes it a lot easier to go to your calculations after that. So here are the steps that I want you to follow for drawing a free body diagram. Okay, first, draw a closed outline of the chosen body. With no external objects in the drawing. Or internal details. No internal details either. The whole purpose of a free body diagram is to be very clear about the distinction between what's in your chosen stuff and what's excluded from your chosen stuff. So that's why you want to draw a closed outline. So like, for example, if scale man is your chosen object, the free body diagram should start with an outline like this. Okay, so this is what it should look like. You can see it's an outline where there's a clear in and out of the line. Some things that aren't good free bodies are like this, because it's not an outline. It's not making a clear distinction between in and out. Or this. Because all the stuff going on the face are internal details and we don't want that. Or the last one is this. And you don't want to do that because the grass and the ground is not included in what we're isolating. And so we don't want it in there. No external objects. Once you have your outline, the next step is to draw a downward arrow. This represents the weight force, and label it either mg, the mass times the acceleration of gravity, or with the numeric weight. So for example, now that you have your outline of the person, and this downward arrow, by the way, should be at the center of the object, you know, coming from the center. So I'm going to draw the downward arrow like that. And you can either label it mg and do that calculation later, or in the previous examples on Wednesday, I think I said this person's mass was 100 kilograms. So 100 kilograms times 9.81 would be 981 newtons. Okay. And now that you have your free body and you have the weight force, the only other forces that are going to show up are these contact forces. So all you have to do now is identify the places where the surroundings make contact with the boundary and then deal with those forces here. So the third step is at each point where the surroundings contact the boundary, draw an arrow in the direction of the force, an arrow in the direction of the contact force, and label it with a value or a variable. So in this case, we have the weight force, and the only place that the surroundings make contact with this boundary is at the ground. And so I'm going to draw a force in the direction of that contact, you know, an arrow in the direction of that contact force. And in this case, I'm going to label it with a variable, and that variable is N. It stands for normal force. We're going to use that for ground forces pretty often. And the benefit of the free body diagram, so this is something I want you to notice, is once you have a free body diagram, it shows you what the force vectors are for every force on the body. And Newton's second law says you add up all the forces on the body, that's equal to the mass times the acceleration. So what that means is that your free body diagram shows everything that goes into the left side of Newton's second law. Remember, Newton's second law says F net is equal to the mass times the acceleration of the object's center of mass. So the free body diagram shows all of these forces that you add up to get F net. Okay, so the last thing we have to do before we can start doing calculations is I just have to tell you basically the directions of different types of forces. Okay, so so now we just need to know how to represent the different contact forces. Um, the, the contact forces are pushing, pulling, and friction. So now I'm just going to go through those one by one, and we'll do examples as we go. So I'm going to start with pushing contact. So when two objects are in pushing contact with each other, that force prevents the chosen object from, let's say, invading the space of the contacting object. Okay, so let me show you a couple examples of what I mean. So right now I'm standing on the ground, okay? The only thing I'm touching is the ground, okay? So if the ground wasn't there, I would be in free fall, right? And so what that force from the ground is doing right now is keeping me from passing into the boundary of the ground, okay? It's keeping me from invading the space of the ground. If the ground suddenly turned to water or something that couldn't support enough force to keep me, I would sink into that space. It's the same thing like if I'm leaning against the board. Like if that board suddenly disappeared, I would invade the space of the board. Okay, so that's what a pushing contact does. So a pushing contact, the direction of this force is always perpendicular to the surface of contact. Toward the chosen body. Okay, so standing on the ground again, if I'm the chosen body, like I'm getting ready to do a Newton's second law analysis on my body, the surface of contact is the ground. So the force that the pushing force is going to be directed perpendicular to the ground and toward the chosen body, which from the ground towards me is up. Okay, so the ground is applying an upward force to me right now. Okay, so let me draw a couple pictures and show you how this works. So for example, if you have two rolling carts, let's say this one is body 1 and this one is body 2. And let's say that there's a 50 Newton force pushing this way and a 100 Newton force pushing this way. Where in this picture are contact forces preventing objects from invading each other's space? Well, there's a pushing contact here from the ground to the wheels. And that also means there's a pushing contact from the wheels onto the ground. There's one here where these two are pushing on each other. And there's another one here at these wheels. Okay, all of those places, if the body touching the object disappeared, the object would go into the space of the other thing. So let's see what free body diagrams look like for both of these. So for body 1, so here's a closed outline of the body. There's a weight force. I didn't say what the mass is, so I'm just going to call this mass of 1 times g. If we knew what the mass was, we could just multiply that out. There is a 50 Newton force that's acting on the boundary that we're given. We don't have to think about that. We can just put it in here. But notice that 100 on the other side isn't acting on body 1. It's over here on the boundary of body 2, so I'm not going to put that 100 in there. Okay? And now I'm going to go around the boundary looking for contact. Well, down here at the wheels, there's contact from the ground. I could put them at both wheels, but I'm just going to lump it into one thing. We're still thinking of everything as particles. So really everything's happening at the same point right now anyways to us. So what's the direction of the pushing force from the ground? It's perpendicular to the ground, perpendicular to the floor, toward the chosen body, so this way. And now I just have to give that a variable name. I'm going to call it N for normal force, and I'm going to give it the subscript 1 because I'm going to use N2 for the other one. So that's the first place where the surroundings make contact with body 1. And then the second place where the surroundings make contact with body 1 is over here on the right side. That's a pushing force. It's perpendicular to the surface, toward the chosen body. So this way, and I'm going to give that the name R. These N's stand for normal force. I'll usually use those for like ground contact forces. And then this R stands for reaction. That's the other variable that you usually use for pushing contacts. But just remember, those are just variable names. If you wanted to call them I or X or N or something like lowercase n, whatever, like nobody could argue with that. They're just variables. And now I'm going to draw a free body diagram of the second body. There's a weight force down. And that is the mass of body 2 times g. So I'll just call that m2g. On the boundary of this body, the 100 Newton force acts, but the 50 doesn't. So I'm going to put the 100 in over here. Okay. And now there's 2 pushing contacts on body 2. There's one at the wheels from the ground. So that's perpendicular to the ground, toward the chosen body. And I'll give that the name N2. The subscripts are just saying that those are different variables. And then the second pushing contact is where it touches cart 1. That is perpendicular to the surface, toward the chosen body. And the last important thing to notice here is these two, I'm going to give the same variable name. The N's are different, but these two are the same. So what's going on there is, so this is an important thing to remember. Whenever bodies A and B, just any two bodies, are pushing against each other. The force on A and the force on B have the same magnitude. And so what that means, kind of practically speaking, is to use the same variable. Those values are going to be the same. Okay. Well, notice that that's different than what's happening at the ground. Okay. The ground is pushing on body 1, and the ground is separately pushing on body 2. That's not the same thing as those two bodies pushing on each other. Okay. So, but it's, yeah. Anybody have any questions? So that's it for how to deal with pushing contacts. Yeah.
Are the 50 and 100 also pushing forces?
Yes, those are also pushing forces, but those like you don't really have to think about because it just tells you what to do with it. But the idea is that, so you would see that if like in an engineering type problem, maybe this is connected to some machine that they've already calculated is going to produce a force like this. So they just tell you the value instead of that being something you have to calculate. Any other questions? Yeah.
So their reaction force is the same. The reason that one moves is because it has less mass.
Yeah, that's right. It's because of other stuff going on, and often that other stuff just has to do with the masses of the two. That's right. Exactly. Yes.
Is the reason why the reaction variables are the same because of Newton's first law?
Third law. Yep, that's exactly right. Yep. So Newton's third law, I mean, I'll bring it up, for your notes later on. But Newton's third law is the one that says for every action, there's an equal and opposite reaction. And what it says is when body A is applying a force to body B, then body B has to be applying a force with the exact same magnitude and just the opposite direction to body A. But we'll talk about that in more detail later on. Any other questions? Okay, so the next one is pulling contact. By the way, Newton's first law, we'll talk about in lab, although it's not very useful for calculations. But Newton's first law is the one that says, the text you've probably heard is an object in motion tends to stay in motion unless blah, blah, acted upon by an outside force. So Newton's first law says if there's no forces acting on an object, it just keeps moving however it was moving before in a straight line with a constant speed. In other words, it takes a force to cause an acceleration of any kind. Okay, so pulling contact. This one we're going to think of as forces applied by cables. And to identify this kind of force, this is when the point of contact could be replaced by a cable or a string without changing the behavior of the system. So that would not be the case in a pushing contact. Like notice that if you move these apart a millimeter or something, a tiny little amount, and then put a string in, replace that contact with like a little tiny bit of string, and then you apply these forces, that string would just compress. And those two things wouldn't even be touching, you know? And so that would totally change the behavior of this system until that string compressed enough that they ran into each other. Okay. A pulling contact, on the other hand, like if something was pulling on my shirt, you could replace that with a string and it would still make my motion happen the same way, you know? So when you have a pulling force, we're always going to think of it as being applied by a string or a cable. And the direction of a pulling force is always parallel to the cable away from the chosen body. So the big fundamental difference is pushing forces act toward the chosen body, pulling forces act away from the chosen body. Okay. And so let's see how this works. So as an example, I'm going to do two carts again, but this time I'm going to have them connected by a cable. So I'll say this is cart 1, and then there's a string cable, and then this is cart 2. And let's say that there's a 300 Newton force applied this way. So let's see what the free body diagrams look like. So first for body 1. There's a weight force. This time, let me give these masses this time. Let's say M1 is equal to 20 kilograms and M2 is equal to 30 kilograms. Okay, so cart 1, the weight force is 20 times 9.81. So 196.2 newtons down. And now that we have the weight in there, we just have to go around the boundary and make sure we account for every place that the surroundings contact the boundary. One place is at the wheels. Is that a pushing or a pulling contact? Pushing, yep. And so just like before, that's perpendicular to the ground toward the chosen body. And we don't know what that is yet, so I'm just going to call it N1. That's something that we would have to calculate. And then the only other place that the surroundings contact the boundary are at the cable, connecting them. Cable forces are always pulling forces, so this is parallel to the cable, away from the chosen body, and I'm going to give that the variable name T for tension. And you know when you're done, because if you go all the way around the boundary and you've accounted for every contact point and you've accounted for the weight already before that, then there's nothing else, you know you're done. Okay, so you can always just sort of do that mental check if you've accounted for every point. What about the 300 Newton force? That isn't touching the boundary of body 1, so it doesn't go here. It will go in body 2 when we do that free body diagram. Okay, so free body diagram of body 2. There's a weight force down, and that's 30 times 9.81, so 294.3 newtons. And then there's a 300 Newton force that's given. And then there's a pushing force from the ground. I'll call that N2. And then the only other place where there's contact is at that cable. So that applies a force parallel to the cable, away from the chosen body, so that way. And then I'm going to give this the same variable name as this one. And the thing to remember here, so again, this is an important thing to remember. Anywhere the same cable attaches to bodies, it applies a force with the same magnitude. And that means that you use the same variable to represent them. This is true even if that cable passes through pulleys along its path. Okay, so let me do an example with pulleys. So let's say we have a ramp and a cart on the ramp like this. And there's a cable that goes from this first cart. Let's say this one's 10 kilograms. And it goes over the pulley, and then that same cable attaches to a hanging mass of 5 kilograms. And let's say that in addition to the weight of this 5 kilogram mass, we're also applying an additional force of 10 newtons. Okay. And I want to draw these two free body diagrams. So first for the 10 kilogram. There's a weight force of 10 times 9.81, so 98.1 newtons, and that just goes straight down. The you know, the angle of the incline doesn't change the direction of the weight force. And now I'm going to go around the boundary of this 10 kilogram thing, looking for where the surroundings touch the boundary. There's a pushing force from the ground, okay? And the rules say perpendicular to the surface. Well, now that surface is at an angle, okay, toward the chosen body. So this contact force, come back here. Okay, so that contact force is perpendicular to the surface toward the body. And I'll give that the name N for normal. But that's just a variable, something to solve for. And then the only other place the surroundings contact the boundary is where the cable touches it. So the rule there is parallel to the cable, away from the body, and I'll call that T for tension. And one thing that you will be happy if you are careful about is make sure from your free body diagram you can tell what vectors are parallel, what vectors are perpendicular, and what vectors are neither of those. Okay, so you can tell from looking at this that N and T are perpendicular to each other and that the weight force is neither of those with them. Okay. Any questions about that? And now we'll go to the hanging mass. So here's an outline of the body. The weight force is acting down. That's 5 times 9.81, so 49.05 newtons. And now at the bottom, we're told that there's a 10 Newton force, sorry. So I'll put this 10 in here like this. And then the only other place that there's contact is the cable. That's parallel to the cable, away from the body. And since it's the same cable as this one, even though it passes through pulleys, it's the same cable, so those have the same variable, same tension. Any questions about that? Okay. Want to see something cool about pulleys? So have you ever heard of pulley advantage? Have you ever heard that term before? So I remember this being confusing to me when I took Physics 1, because I'd always heard that pulleys had this ability to reduce the force that you have to apply to lift things. You can use pulleys to lift heavier things by pulling less hard. And it's true that you can use pulleys that way. So this is pulley advantage. But it's not really about the pulley specifically. It's really just about a certain smart way to configure pulleys. But I want to show you how this works kind of. So let's imagine that there's a ceiling here. And let's say that there's one pulley connected to the ceiling like this. And then another pulley here that's connected to a mass. Okay, let's say this is 50 kilograms. And the cable that goes through these pulleys connects to the ceiling here, goes under this pulley, goes up over this pulley, bless you, and then is pulled like this, okay? So it's all one cable going around this whole thing. If you cut this cable, this 50 kilogram mass would fall down to the ground. And so the question is, you know, the weight of this thing is 490.5. What's the force T required to hold this at rest, you know, to keep this from dropping? Okay. Well, if this setup just had one of these two pulleys, like say, so this cable that has the T at the end of it, if that cable just went over the pulley attached to the ceiling and then connected straight to the mass, it would take 490.5 newtons of force to hold it up. Okay? And that sort of makes sense. You know, that's kind of what you would guess is going to be required. But we're going to see with this setup, that force is cut in half. You can hold this thing up, not let it fall, by applying a force of 245.25. Yeah, I think that's right. 245. Yeah, 0.25. So what I'm going to choose as my free body is this. Okay, so that means that the thing I'm isolating has a little strip of cable that goes under the pulley. Okay, and it also includes that hanging pulley, and it includes this mass. And the free body diagram looks like this. So I'm going to draw the closed outline. The weight is 50 times 9.81, so 490.5. Cable applies a pulling force to itself, so there's a force T here and a force T here. That's the same cable. And now where we're heading with all this stuff is now we're going to be able to put this all into Newton's second law. So let's think about Newton's second law here. And I'm just going to think about the y direction, you know, up and down. So we have two of these T forces pointing straight up. So we have T plus T. Acting down, we have 490.5. Newton's second law says that's equal to the mass times the acceleration, but we're just holding this in place, so there's no velocity and no acceleration. And so what we get is that 2t minus 490.5 is equal to 0, or t is equal to 245.25. So that's pulley advantage, but it doesn't come really from the pulleys. It comes from the way you set the pulleys up. Okay, and then the last type of force is friction force. There are two types of friction. The first one is called static friction. Static friction. And static friction prevents an object at rest from starting to slide. Okay, so like this stapler, it's at rest. I can't apply too much force before it starts to slide, but right now I'm applying a little bit of a horizontal force to it, and that friction is what's keeping it from starting to slide. Okay. Then the other kind of friction is called kinetic friction. And that's when an object is already sliding. And friction tries, not trying to give friction human character traits, but the friction tries to slow it down. The friction is always acting in a direction that would tend to slow it down. So that's like when this is moving, I'm applying a force to it. It should be accelerating as I do this because I have a force going this way. So Newton's second law says it should be accelerating. It's not accelerating though because the friction is fighting that. The friction is trying to slow it down. Okay. There's no reason we couldn't talk about both of these two calculations, but we're just not going to in the interest of time. So we're going to skip static friction. And we're going to only do kinetic friction. Okay, so one thing to remember about friction is, so friction always acts together with a pushing force N. That pushing force is what forces the two surfaces together. Okay, so with friction, it's a little different than the other two. I'm going to tell you the direction of the force, but I'm also going to tell you something about the magnitude of the force. So the direction of a friction force is always the opposite direction of the velocity. Which means that for friction problems, you always have to be given the direction that the thing is sliding. Okay, you can't do it without knowing that. Opposite direction of velocity, that's how it's slowing this thing down or trying to slow it down. It's always acting in a direction that's trying to slow it down. And then the magnitude is always equal to this value mu. That's the Greek letter mu. This is the easiest one to remember because mu is spelled mu and it looks a little like an M and a little like a U, times the normal force. So that's always the magnitude. And I'll tell you what this mu means. It means, so it's a positive number. Kind of representing, you can think of it as kind of like stickiness between two materials. It almost always ranges between 0 and 1, but there are actually some with coefficients higher than 1. But for, where do I have this written? For ice sliding on ice, you would think that that would be a pretty low amount of friction. And that gives you a coefficient of friction of about 0.02, so pretty close to 0. Whereas rubber on concrete, that gets a pretty good grip, you know. That's why tires are made out of rubber. And the coefficient of friction for that is about 1. And sorry to make you squeeze this in here, but I didn't write this before. This is called the coefficient of friction, this mu. Okay, so let me do an example of this one. So let's say that a block is on an incline like this. And let's say there's a 30 Newton force pushing this way. And let's say that the direction of motion at this instant is this way. So that's the direction of the velocity vector. And let's say this has a mass of 10 kilograms. And let's say that between the incline and the block, there's a coefficient of friction of 0.3. And we want to draw a free body diagram of this. Bless you. So the first thing I want to sort of point out or clear up, you might look at this and think it doesn't really look possible because this 30 Newton force is trying to make this slide down the ramp, and the weight is kind of, part of the weight is trying to make it slide down the ramp. But I told you that the direction of motion is this way, okay? So like, how can that be? Well, remember the direction of motion is the velocity. And the velocity does not depend on the forces happening at that instant. It depends on the forces happening at previous instants. Okay, so basically the way this would happen is if someone gave this a shove up this ramp and then these forces were applied, you know, and so it's sliding up this way, but these forces are changing the fact that it's sliding up that way. Okay. Okay, so free body diagram. So there's the block. There's a weight force of 10 times 9.81, so 98.1 newtons. There's a 30 Newton force that's given. There's a pushing force from contact with the incline. That's always a companion to friction. So this follows the rules of pushing, perpendicular to the surface, toward the chosen body, and I'll call that N. And then last, there's a friction force that's opposite the direction of motion. So it's this way. And the magnitude, the label that I'm going to give this is 0.3 times N. Let's see. Anybody have any questions about that? I want to tell you just sort of intuitively, like, why is it that the magnitude of this friction force depends on that N? Okay, because we haven't seen I don't think we've ever seen a force like that where one force depends on another one directly like this. But the way that works is, I think it sort of makes sense intuitively that the harder I push down on this stapler, the more the ground is pushing up to keep it from sinking in. Okay, so when I push down on this stapler, it's making that N force get bigger. And I think it makes sense to all of you that, like, if I'm not pushing down on this, it's pretty easy to slide it, you know? But if I put all my weight on it and ask someone to come over, it would be pretty hard to push it side to side, okay? So the bigger that N force is, the bigger that friction force is, and that's the way that works, okay? Well, let me give you a problem, and you can try to think through doing free body diagrams. So let's say we have a ledge with a pulley. And there's a block over here with a mass of 2 kilograms. And a hanging mass over here of 1 kilogram. And let's say for the 2 kilogram cart, the coefficient of friction is 0.1. And the direction of motion, let's say, is this way. So take a minute and see if you can draw free body diagrams for both of these. Okay, so I'll start with the hanging one. There's a weight force of 1 times 9.81, so just 9.81 newtons. And the only place where there's contact with the surroundings is the cable, so that's parallel to the cable, away from the body. And then that one's done, and then we'll go to the second one. There's a weight force of 2 times 9.81, so 19.62 newtons. There's a pulling force from the cable, so parallel to the cable, away from the body. It's the same cable as this one, so this has to be the same variable. And then there's a pushing force and friction force pair at the ground. So the pushing force is perpendicular to the surface toward the body. I'll call that N. And then the friction force is opposite the direction of motion. So this way. And the magnitude is 0.1 times N. And one thing I want to say is it can get a little confusing with forces being given in newtons, and then also these normal forces are capital N's. I'm going to always, you can tell from my notes which is which, because when I do normal forces, I'm always going to put the fancy outfit on it with the hat and shoes, and regular newtons, I'm just going to do like a regular capital N. So look for that. But remember that this is always a mistake that people make on the first test with this kind of stuff. The N here in the friction force, that's not newtons. That's times this normal force. Okay, any questions?
So the pushing force is always perpendicular to the object?
Yes, it's always perpendicular to the surface, and it's always perpendicular to the friction force, because the velocity always has to be along the surface, so the friction force has to be along the surface too in the opposite direction. Okay, that's all.